Let's move on to another setting, just to settle the concepts. Again, a setting which is very familiar. Okay. Let's look at the setting of dice. Okay, here's an example constructed by the Soviet and Russian mathematician S. Bernstein. Imagine that a die is thrown twice. Of course, we imagine that it is a fair die, that it has got 6 faces. The faces are numbered 1 through 6. We immediately then identify the sample space by identifying a system of ordered pairs, J and K, let us say, where J represents the face shown by the first throw of the die, K, the face shown by the second throw of the die. Of course, J and K are integer values running between 1 and 6, and therefore there are 36 possibilities for these pairs. The sample space has got 36 elements. Let's look at some events that we can construct from this experiment. So let A be the event that the first throw shows an odd number. In other words, the first throw shows 1, 3, or 5. Let B be the event that the second throw shows an even number. In other words, the second throw shows a face 2, 4, or 6. Now let's put together a composite event C, where C is the event describing the attribute that the sum of the face values in the 2 throws is an odd number. Remember, the face values will add up to values between 2 and 12. So the sum of the face values being odd will correspond to all pairs for which the sum is 3, 5, 7, 9, or 11. Well, we have 3 events here, but before we proceed, let's identify the probability measure, and naturally enough, the die is fair, the repeated throws are independent, whatever that means. And what, in our context, we will identify this is to say that you have 36 atoms in this experiment. It is going to be a combinatorial setting where every atom is equally likely, and therefore all atomic probabilities are 1 in 36. And again, the question, are these events A, B, and C independent? Pause the lecture and run a rule through the definition to see whether you can check on whether this in fact is valid. All right, now let's come back and identify all the events of interest in this problem. So let's start with the event A. The first face is odd. That means we're looking at all the ordered pairs J and K, where J is an odd number. In other words, J is 1, 3, or 5. What about K? Well, K could be anything whatsoever. In other words, we're looking at ordered pairs of the following characteristic: 1, 1, 1, 2, 1, 3, and so on through 1, 6, 3, 1, 3, 2, and so on through 3, 6, and finally 5, 1, 5, 2, and so on through 5, 6. Okay. What is the probability of this? Well, since the first element can be specified in 3 ways, the second element is unfettered, can be specified in 6 ways, there are 3 times 6, or 18 ways of specifying such ordered pairs. 18 out of 36 gives you a chance of 1 in 2. It's very comforting because, of course, we understand that the event that the first phase shows odd, by symmetry, should have the same chance as the event that the first phase shows even. But, of course, it is comforting to have the formal calculation verify this intuitive and correct answer. Let's quickly run through B. The event B describes a setting where the second throw shows an even face, which means you're looking at all ordered pairs. Remember, events are subsets of the sample space. The sample space here is a space of pairs. Which ordered pairs tick the box for B? Well, you look at all ordered pairs J and K, where K is an even number, 2, 4, or 6. And of course, J could be anything whatsoever, 1 through 6. Again, the chance of this, there are 6 possibilities for the first element, 3 for the second. Therefore, there are 6 times 3 or 18 possibilities in favor of the event B out of 36 possibilities, and therefore B, again, naturally and inevitably, has got a probability of 1 and 2. What about C? A little more complex, but we can break this down. Remember, again, C represents the event that the sum of face values is odd. Our first rule of business is to identify those pairs which trigger this event. Remember, again, C has to be a subset of pairs. Which pairs? Well, if a sum of 2 integers is odd, that must necessarily mean that one of the integers is even and the other is odd. But this can happen in 2 ways. J could be even and K odd, or J could be odd and K even. What are the chances of this happening? Well, J odd, well, there are 3 ways of J being odd, 1, 3, or 5. K even, well, there are 3 ways of K being even, 2, 4, or 6. And therefore, there are 3 times 3, or 9 ways for J being odd and K being even. And by the same kind of argument, there are exactly 3 times 3 ways, or 9 ways, of J being even and K odd. Altogether, you have 9 plus 9, or 18 outcomes favorable to the event C out of 36, and again, C has got a probability 1 and 2. A little introspection should tell us, oh, this is also to be expected. Again, there is full symmetry in this game, and therefore, about half the time we should get an odd sum, and about half the time we should get an even sum, and the calculations support this. Let us now consider intersections of pairs of these events. What does it mean to say A intersection B? This means that the first face shows an odd number, and on the second row, the face shows an even number. In other words, we are looking at ordered pairs J and K, where J is odd, there are 3 possibilities, K is even, there are 3 possibilities. Therefore, there are 3 times 3, or 9 possibilities out of 36, and therefore, the chance of A intersection B is 1 in 4. But a very similar argument works for A intersection C and B intersection C. Let's take a look at A intersection C for our definiteness. A represents the event that the first face is odd. C represents the event that the sum of the face values is odd. But if the first face is odd, J is odd, and the sum of J and K is odd, that forces K to be even. And therefore, A intersection C is precisely that collection of ordered pairs J and K, where J is an odd number, 1, 3, or 5, and K is an even number, 2, 4, or 6, and again there are 3 times 3, or 9 possibilities. Out of 36, it's again 1 in 4. And B intersection C, likewise, is again ordered pairs J and K, where J is odd and K is even. In other words, A intersection B, A intersection C, and B intersection C are all exactly the same event. The English description on the left gives you different flavors of this event, but they all describe exactly the same object, and therefore it is not at all surprising that all these objects have the same probability, 1 in 4. What about A intersection B intersection C? The first face is odd. The next row shows an even face, and the sum is odd. But if the first face is odd and the second face is even, the sum is forced to be odd. This is another way of saying that the event A intersection B is contained in or implies the occurrence of the event C. And therefore, A intersection B intersected with C is just A intersection B itself, which means that A intersection B intersection C consists of all pairs where J is odd and K is even, and there are exactly 9 such pairs, which gives you a chance of 1 in 4. Okay, let's pause now and see how we're doing with our rule of products. 1 and 4 is surely 1/2 times 1/2, and therefore for all pairs A and B, A and C, B and C, a rule of products is manifested. But for a triple, 1/4 is manifestly not 1/2 times 1/2 times 1/2, and therefore a rule of products is violated when you have the 3 intersections. What we have discovered is A, B, and C are pairwise independent, but they are not independent jointly. Right? When we say independence, when there are many events floating around, we'll always mean jointly, and we'll drop the descriptor. Okay. So, the moral of the story is that independence is a rule of 4 properties when we are talking about independence of 3 events. Our examples have led us to conclude that independence certainly implies pairwise independence. If all 4 rules are satisfied, then manifestly the first 3 are satisfied. So when you have joint independence, pairwise independence is implied. But just having the first 3 of those properties satisfied does not imply that all 4 are satisfied. Pairwise independence does not imply independence in general. And indeed, these 4 relations that describe independence for 3 events at a time are inseparable in the sense that no 3 of them imply a 4th. I will let you explore examples along these lines in your problems for solution.